Okay, continuing from last time. Iterative methods. That's where we were. That's where we were. We saw the saw the Richardson method, the Jacobi method. We wanted to prove Gauss Siedl. Let's see what can I remember about Richardson method. Richardson methods will work if the eigenvalue is between 0 and 2. The eigenvalue of what though? The eigenvalue of our matrix A. Why was this the case? Because I make my G is identity minus A, right? Yes. And this will only hold, and I want to make my row of G less than 1. So the row of this matrix should be less than 1. And that's okay. How about Jacobi? Jacobi will converge for a strictly diagonally dominant matrix. How though? Can I remember any results? This is something that I remember. If my x is x plus 1 is gx plus c, my g was I minus q inverse A, and my c was q inverse B, right? How do I remember this? If I put q equals to A, then this is A inverse A, identity is subtracted, q in A inverse B, so it's one step directly. So that's okay. So this is it. So for Jacobi method, I choose q as the diagonal part of my matrix A, and it will converge if it's my strictly diagonally dominant. I check the row of this matrix G, and I took the infinite norm to conclude that if the infinite norm is less than 1, that means the eigenvalues are definitely less than 1. So it converges. Then we move to the Gauss Siedl method, in which we chose Q as the L and the diagonal part of my matrix, leaving this as 0, the upper part. This was my Q. When does this converge? Yep. So I remember this. Common choices Q. Jacobi method I remember. Choose Q is D plus F. The Gauss Siedl method converges for any starting point x0 if A is symmetric, positive, definite. This is something that we prove. When does Gauss Siedl converge? Just a minute. Yeah. So my Gauss Siedl, yes. My Gauss Siedl method will converge. This is the claim of the theorem. If A is SPD, then choosing Q as D plus L inverse and choosing G as I minus D plus L inverse times A, the row of G is less than 1. This is something that, that's how we prove, right, convergence, by saying that the eigenvalue is less than 1. So let's look at the first step. Identity minus D plus L A, I write my A as D plus L plus R. D plus L plus R. This becomes identity minus something minus. So minus D plus L inverse times R. This is my G. Minus D plus L inverse times R. That's my G. Jamie, like my G. So for any SPD matrix A, we have a scalar product. For any B, we have the adjoint in A. So that, self-adjoint is positive with respect to A. If a self-adjoint matrix is positive, then show that let G with adjoint G star, then if B is 1 minus G star G, if B is 1 minus G star G is positive with respect to, it follows that row of G is less than 1. Proof. I want to build some intuition about why this statement is true. If this statement is true, then all we have to do is just plug and chug and it will work. But then this is something that one needs to have an intuition about, right? Why is this the case? Let me go from bottom up. If B identity, this is just the definition of positive, right? Self-adjoint is positive. Okay, so the meaning. Right. So first let me look at the inner product. I have something cooking in my brain. Let me just look at the inner product. The inner product is xy a weighted inner product. This is just x times ay in the two norm product, right? And this is just x transpose ay. This is just the definition of this, right? Now I want to write its adjoint, and adjoint is defined in such a manner. I mean, a matrix has this adjoint. If bx y a weighted is equals to x times b star y a weighted, and they both are equal. So let me look at this. This becomes x transpose b transpose. Is that transpose? Is it only for real? It's my notes say it's only for real. So let me just let me assume that it's only for real. B transpose ay. This is same as x transpose a b star y. That means B transpose A is equal to A B star. Therefore B star is A inverse. B star is A inverse B transpose A. B star is A inverse B transpose A. That works. I've derived for myself the definition of an adjoint in the A weighted product. So a self-adjoint matrix is positive. Self-adjoint means B is B star. It's just definition. A self-adjoint matrix is positive if its inner product with A is greater than 0 for all. So it's like it's a positive matrix, right? Now let's show the G with adjoint G star. Then if I define B as this, and this is a self-adjoint, if B is a self-adjoint matrix, if B satisfies this, that is positive, then it follows that rho G is less than 1. Let's see. First of all, let me show that B is equals to B star. B equals to I minus G star G, right? Where G is the adjoint of G. Oh, G star is the adjoint of G. They are not self-adjoint with each other, right? I have to show that this is positive first I have to show that this is self-adjoint, and the definition of adjoint B star is A inverse B transpose A. Let me put that in here. A inverse identity minus G star G transpose A, right? Identity transpose is identity, so A, this is just I minus, right, I minus A inverse G transpose G star transpose A. Now let me write G star from here, and G star transpose will be from here. G star transpose will become A transpose. G star transpose will become A transpose B and A inverse transpose. Or should I just write G star? I mean, what if I substitute G star directly? Okay, let me think. I minus G star G. What is B transpose? B transpose is I minus G transpose B star transpose, where B star transpose is A transpose. Well, A, oh yeah. A is a symmetric matrix, right? A is a symmetric matrix. Oh, then that's okay. Let me just write G star transpose. G star equals to A inverse A inverse G transpose G. The transpose of this is A transpose G, A inverse transpose. Now I can just remove the transposes from both the sides. It just becomes AG A inverse. So let me write that. AG A inverse. A inverse A gets cancelled with each other. A inverse G transpose A is nothing but A inverse G transpose A is nothing but the G adjoint. So this is equal to, okay, so this matrix is self-adjoint. Now I have to prove that this matrix is self-adjoint. That's proved. I minus G star G is a self-adjoint matrix in the A inner product. Now I have to prove if B is positive. If B is positive, then the row of G is less than 1. How to prove that B is positive? B is positive when Bx inner product with any other with inner product A. So Bx x A inner product equals to identity 1 xx A inner product minus G transpose G. So I write, G adjoint G. G adjoint G x x A inner product. Oh yeah. So this, if B is positive, if this is greater than 0, that means so Gx norm square is greater than x norm square less than. Gx norm square is less than. Why did I write this? I can bring the G adjoint on this side, and this basically becomes Gx in the A product. That's how adjoint is defined, right? If I move A from, where did I write adjoint? Yeah, I move adjoint from being on the right side of the comma is equals to being the adjoint on the left side of the comma. So yeah, x is greater than Gx for all x not 0. That's the definition of positive. But this is the A weighted inner product. Is greater than, so in that case, sure, the norm, I mean the A weighted norm of G is always less than 1. That's okay. But that's the A weighted norm. Is there any comment about that then? I have to ask this question then. Because this is the A weighted norm. Everything is A. So does A weighted norm being satisfying this in any norm, does that work? Well, I think it maybe it does. Okay. Okay, so if B is positive for such a scheme, that is I minus G star G, if a B is positive, then it works. For Gauss Siedl, I will choose my G as identity minus D plus L inverse A, right? That's my G, that's my choice of G. So now I want to show that the row of G is less than 1 or the norm of G is less than 1. And from the result, if I can show that I construct a B that is I minus G star G, and if I show this B is always positive, in that case I will always work, that this will always work. So let me construct my G star. Right. Let me construct my B then. Let me see if my B always holds. For that, let me first construct G star. G star is A inverse G transpose A, right? And G is equals to identity minus B plus L inverse A. Let me plug that in here. A inverse G transpose is identity transpose minus something times A. Can I take transpose inside the? Can transpose be taken inside this? Seems that way. So this becomes A transpose D plus the R part inverse. A transpose D plus R inverse, right? A inverse A becomes identity minus A inverse A transpose. I'm doing it. A inverse A transpose D plus R inverse times A. And because A is a SPD, A is an SPD, A transpose is equals to A, so this gets cancelled. So this is identity minus B plus R inverse times A. That's just my G star. And now let me plug G star in. My G is there, my G star is there. Let me remove this, clear it up for calculation. And let me just put, now let me just create G star G, because I want to make one my identity minus G star G. So G star G, oh, now multiply these two together. Okay. I minus B plus R inverse A times I minus D plus L inverse A. Identity minus plus D plus R inverse A, D plus L inverse A. Right. If I write my A again as D plus L plus R, the D plus L plus R here, and I write my A as D plus L plus R here. The D plus L gets cancelled with the D plus L results in identity. This becomes identity minus, so this becomes identity, so this identity will get wiped out and it will result in D plus L inverse R, right? Another minus identity will come up here and D plus R L, right? Now if I put if I do some mathematical magnificence, my answer will come out to be B is equals to D plus R inverse D plus L inverse A. Yeah, it can come. If I just expand this A, I think it will cancel out all the way. I think it will. For example, D plus R inverse L. But then I'm sure it will come. I'm sure this is nothing. So now I do the yeah. Well, this is true. The entire calculation just says that the row of that B is positive in the A inner product. Oh, in fact, B is positive overall here in the two inner product, and therefore rho of G is less than 1. So was this the case? But then we define positive for A inner product, right? Rho of G is less than 1. Theorem is, after all that, something that I will remember, something that I will just, choose to remember, is an iterative. It's just the idea of this entire thing is that we're doing iterative processes. We're doing iterative processes because sometimes we don't want to do the full linear thing. We don't want to solve Ax equals to be properly. And if you're only gonna get to machine precision, might as well just do iterative methods. So if A is a symmetric positive definite, Gauss Siedl method converges from any starting point. And D plus L, and Gauss Siedl is choosing D plus L. Sure, the down part and the L part, sure. Okay, now relaxation methods. Use linear combination between new and previous iterates. Where omega greater than 0 is a damping parameter leading to over relaxation. Target is choose W such that rho G is minimal. Let me see what's being done here. I choose xk plus 1 omega times g xk plus c plus 1 minus omega times xk, right? Now a fixed point method is called symmetrizable if for any symmetric positive definite matrix A is only for SPD matrices A, the matrix I minus G is similar to one SPD matrix. That is, there is a regular W such that W I minus G W inverse is SPD. Why is there a need for this? Let me see if there why was there a need for this? Okay, let me see what happens here. Omega G xk plus omega C plus identity times xk minus omega times xk, right? This is just 1 minus omega times identity times xk. What I want to do is just pull the xk terms together. so that I can write this as an entire new matrix. So this becomes omega G plus identity minus omega identity xk plus omega c. That's all. Right? Omega c. Omega g plus 1 minus omega. That's it. Now, this is, I am seeing something like identity minus omega times I minus g xk plus omega c, right? This is if I include an omega damping parameter, right? Xk, I pull xk outside, it becomes identity minus omega times I minus g. So there is some mention of I minus g. How should I choose? Okay, so now the point is choose omega such that the rho of this is minimal. Let's see. What's next here? Let's see. I understand. Why was this necessary though? Regular W such that this is SPD. Why was this needed though? Symmetrizable need that I minus G is similar to SPD matrix. I minus G. Why do we need this symmetrizable? The result that's written here is we can make any symmetrizable iteration method convergent for SPDA. We can make any symmetrical method convergent for SPDA. Why do you need it to be symmetrizable though? That's my question. Let's not think about this. Let's come at it from another angle. Let's just try to work with here. My G omega becomes omega G plus 1 minus omega times identity, right? So I want to know the eigenvalue of this. Eigenvalue of G omega is omega times lambda I of G plus 1 minus omega, right? Right. This becomes whatever. 1 minus, yeah, 1 minus omega, I just wrote this up, right? 1 minus lambda Ig. This is the eigenvalues of my new thing, right? Okay. Now I want this one minus omega, 1 minus lambda Ig. So let me plot this. Let me see what this function looks like. In term, I'm gonna fix omega, and I'm gonna plot in terms of the eigenvalues of G. I'm gonna use this as my x-axis. 1 minus x is something like this. Omega times is just doing this omega times, something like this. Flip that is something like this. And 1, add 1 to it, so it's something like here. Something here, right? Okay, let me try to plot this. What I want is that the modulus of G of omega mod should be less than 1. So let me try to plot this. Okay. One minus omega times 1 minus lambda 1 minus x. Let me plot in terms of x, right? And I want to see the modulus of this. So let me see here. If my omega was 1, omega 1 means just the normal thing, yeah. So just the normal, no relaxation, no relaxation whatsoever. So what this graph tells me for omega greater or equal to 1 is that the modulus of my G omega is the same as I mean it varies extremely similar to the modulus of my x, right? Let me try to change omega a little bit. Let me say that I damp a bit. Yes. For 0.7, this is what it looks like. For example, if my eigenvalue was minus something, if my eigenvalue was minus 0.429, then for omega 0.7 the rho of G will be less than 1. I mean it will be 0. I want it to lie beneath 1 actually. So this is where I want my all of my rows to lie actually. And this will only happen if my x's lie between these two numbers. This is what I want it to be like. For a given omega, if my eigenvalues of matrix G lie between these two numbers, then my eigenvalues of this matrix will always be less than 1. So by changing omega, what I notice is that the x-intercept is always 1, 1. So my eigenvalue of my G matrix should always be less than 1. That's what they want it to be. That's like the main condition. If I had an eigenvalue greater than 1, then no matter what omega I choose, I will never be able to, get it to behave in this manner. Oh, but what if I choose a negative omega? This is only true for positive omega then, right? Well, for negative omega, it means that omega always has to be positive, right? Is that made clear somewhere? Yeah, omega greater than 0 is a damping parameter. It's always greater than 0. So my lambda of G should always be less than 1. In that case, I will be able to find an omega that makes my method convergent, right? If my omega positive, that's what I learned from the graph, right? For omega positive, if I say that, let's say, if my eigenvalues of G are less than 1, they can be anywhere on this axis, like anywhere. Whatever is the leftmost eigenvalue and the rightmost eigenvalue, the leftmost eigenvalue and the rightmost eigenvalue, I can, if my x's lie between this, I can choose an omega, for example, let's say 0.3, such that the modulus of my new eigenvalue in this range is less than here. That's how. So given a lambda max and given a lambda min, I can choose an omega such that rho of G is always less than 1. Cool. Let's say I was given my lambda max as minus 10. Let's see. If my lambda max was minus 10, what would happen? Yes. If my lambdas of my G were between 1 and minus 10, let's say I choose my omega is 0.18. By choosing my omega is 0.18, the rho of my new, but the rho of my relaxed GW is always less than 1. Cool. So this is the only need that the eigenvalue of G should be less than 1. That's the only need, right? The eigenvalue of G should be less than 1. Now why does that necessitate this to be symmetrizable? I minus G. Also, where did I use that A was positive symmetric definite? I did not use that A was positive symmetric definite anywhere. To say that eigenvalue of G is less than 1, yep. So this is something that's understood. The spectrum of G, eigenvalues of G should lie between minus infinity to 1. If that's the case, then I can always choose. So because I minus G is similar to an SPD matrix, all eigenvalues are real and positive. So 1 minus lambda is greater than 0. So lambda is, okay, this is fine. Then I minus G has all of its eigenvalues greater than 0. And similarity to an SPD matrix just guarantees that, right? So I minus G, but then this SPD, this specifying matrix A to be SPD is something that I do not understand, right? What else was I not able to get clearly? Yes, I want to write these in notes actually. New notes, NM1 doubts, Gauss Siedl proof, positive with A weight A inner product, norm G less than 1, in A norm. That's what we got, that it's less than 0 in the A norm, right? For Gauss Siedl method, we got that the norm is less than A norm, but then we prove I minus G star G positive in 2 norm. So does that hold? Next is why need of a SPD in symmetrizable relaxation methods sufficient to say eigen of G is less than 1. Okay, that's my second question. If I just say that eigenvalues of G are less than 1, in that case it works, right? Because I'm done there. Yeah. Now we see, given the spectrum, if I knew the spectrum of G where all eigenvalues of G are less than 1, how would I choose my omega? I choose my omega such that my rho of G omega is minimum. And it's 1 minus omega, 1 minus lambda, right? So there can be two endpoints we saw, the lambda max and the lambda min, right? Here, let's look at what is this, bro? I'm not able to understand. Let me think. I'll be able to get it, no problem. 1 minus lambda times 1 minus omega, 1 minus lambda. These are the eigenvalues of my G rho, right? So, given an omega, all I look at these eigenvalues. I don't understand this. Solve for omega max is 1 minus lambda max. Okay, I see. Okay, let me just write some things then. Lambda max of G is always less than 1 and it's always greater than lambda min of G, right? That's true. It's a true statement. This is something that I'm comfortable with. 1 minus lambda min of G is greater than 1 minus lambda max of G is always greater than 0. That's I'm comfortable with. That's something that I'm comfortable with, right? 1 minus lambda min is greater than 1 minus lambda max is greater than 0. Okay? That's something that I'm comfortable with. Now, I'm gonna vary this 1 minus lambda. It can either go from 1 minus lambda min to 1 minus lambda max, right? 1 minus lambda max is a small number which goes to 0. 1 minus lambda min is a big number. Okay. So, let me vary my 1 minus lambda to go to the highest number possible. That is 1 minus lambda min. In that case, 1 minus omega, 1 minus lambda min is a small number actually. One minus lambda min is a big number. It is a big number. And I want this what I'm trying to do here is I'm trying to make this as large as possible. Like find omega which makes this the bigger number and find an omega which makes this the bigger number while staying less than less than 1. Okay, I have another approach. As these both numbers are positive and omega is a positive number, omega times these numbers are also positive. Let me just look at this one. Let me try to make this 1. So that becomes 1 minus omega, 1 minus lambda min of G is equals to 1 or minus 1. Omega is omega is 0. If I make omega 0, then both of these eigenvalues are 1. If I make omega 0, all of the eigenvalues are 1. So what if I made omega a little bit more than 1? I make omega a little bit more than 0, they decrease. Both of these values decrease a little bit. What if I put my omega is plus infinity? If I put my omega is plus infinity, positive number, it goes to infinity. So there has to be a cutoff of omega, right? I don't understand this, man. 1 minus lambda min is greater than 1 minus lambda max, and they are both greater than 0. They are both positive numbers. So why do I want to make them equal though? This shit. Jacobi relaxation. Jacobi हो गया मेरे साथ आज. What's here? Conjugate gradient. Let me let me see how long. Nice. 1 hour. What time is it? It's 7 o'clock. So there are some questions in my mind about this. Let's look at let's finish the slides and then we can look at the textbooks to see what they have to say. This video is going to be quite a long video, that's to say the least. Okay, so but I have never in my phone, so it's okay. I don't care. Richardson is just choosing my G as I minus Q. Let me read completely. I minus Q inverse A and choosing my Q as identity. This is Richardson. That's what it's happening. So what's going on in Richardson method? Xk plus 1 is xk plus 1 is xk plus b minus ax. Yeah. So we would like to update, what would we like to update xk with? We would like to update xk in the direction of the error, because if we had the direction of the error, we could directly write the answer in one step. However, we don't have the error, and therefore it's reasonable to use the next best thing, which is the residual. It keeps on updating in the direction of the residual. When does Richardson converge? Richardson will converge when my eigenvalues are less than 2, right? Well, identity minus A, eigenvalues of this should be less than 1. So 1 minus eigenvalue should be less than 1, modulus of this. So eigenvalues less than 2, yeah. For eigenvalues less than 2, 1 minus eigenvalues are less than 1 in the norm sense. And they are positive, so it's okay. Jacobi? What about Jacob? Jacobite iteration? Jacob? Why? I just divided the residual. Let me write the fucking iteration in the algorithmic sense. Xk plus 1 equals to xk minus d inverse A xk plus d inverse B. D inverse B can be calculated first step. Xk plus yi, where yi is xk. Wow, yeah. D inverse B minus AXK. So compute the residual divided by the diagonal and add it to this. So what we do is compute the residual, divide by the del element, and then add in the xk. So in every substep I of iteration k, and update yi is computed and stored. Applied immediately. Thus, with the current approximation, equation I will be solved exactly, and improvement that will be lost in the. However, the updates of a component are not applied immediately, but only at the end of iteration step. Don't know what the fuck this guy's talking about, brother. Let's see. About the Gauss. What's Mr. Gauss doing? Well, this is simpler. Let's go with the backward. X plus 1 is x plus yi. Yi is just the diagonal inverse. Just diagonal inverse of my residual k, and my residual is bi minus how does this work? Why is this though? Why is this bakchodi? I don't like this. Xk plus 1 is equals to xk minus L plus D inverse A xk plus L plus D inverse B xk. What? Yeah. plus L plus D inverse B minus AXK. What I don't understand it is how is it any different from yeah, this will have, I'll have to see in the textbook. I don't understand it from here. Oh, no. B minus AXK. What they are trying to do is they have separated this somehow. They are just adding yi, right, to xk. So whatever this is yi. Well, I understand this because I've written this code. I've coded this, but I forgot. Bitches. Let me see. You know what? Let me see. What homework? This is homework 4, right? Let me see homework 4. Let me see how I previously understood. I would understand with my own. Oh. Oh. It's by writing this actually. Hmm. Hmm. While implementing on code, I will not really compute D plus L inverse, right? I will never really compute inverses, right? I definitely read this from the textbook and that's why I understood it then. There's no way I would have understood it now. Yep. Okay, I'll get to the textbook and then we'll understand this in much more detail. Spectral radius typical iterative matrices. The spectral radius rho determines convergence and speed. The smaller rho, the faster the error decays. In practice, rho is often very close to 1. So that even though rho is less than 1, it takes a reasonable amount of iterations to get a reasonable answer. An important sample scenario is discretized. It is typical that rho depends on the dimension n of the matrix A, and thus in terms of PD discretization, it depends on the mesh width h of the underlying grid. Hooge. Let's look at Jacobi Gauss Siedl from the quaternary textbook. How about this bitch ass textbook? Do they teach Jacobi? There's conjugate gradients, no Jacobi here, so it's only quaternary. Iterative methods on solving linear systems, page 125. A is strictly diagonal dominated by rows. The Jacobi and Gauss Siedl methods are convergent. Jacobi. They're talking about over relaxation like they've already mentioned it somewhere, but I didn't see it. That's the problem with this thing. I want to understand over relaxation. Where have they mentioned over relaxation, man? They talk about over relaxation like they've already mentioned it somewhere. Let me see. No, I think it's just assumptions that the reader knows about the over relaxation stuff. I don't know. I'm very dumbfounded by it. I'm dumbfounded by it. What is your problem, brother? ये क्या चूतिया है क्या बैंड जो? Jacobi. What was Jacobi? Can you recall? Every iterative method is gx plus c, where g is identity minus q inverse a and C is Q inverse B, or it is, let me write it as, are you sure about that? Is it identity minus? Yeah, I should know this. I should know this bullshit. I've been talking about it for 2 videos now. Bitches. Yeah, I was right, but I'm still stupid. Gxk plus 1, q is q minus a xk plus b. Right? This is every method ever. For the b plus l, xk plus 1 equals to minus r xk plus b, right? That's what it becomes, right? For so b plus l times xk plus 1 equals to r xk plus b. So the first element is computed by this. To compute the second element, we already used the first computed elements thing. We used the first component, the first computed component. So it's like while doing Gauss, where you to compute the jth element of this vector, we use all of from 1 to j minus 1 elements. That's okay. This is only thing. That's all I can get from this textbook. Other than that, it's just convergence result of the over relaxation a priori forward analysis, which is something I don't want to do. I'm tired now. I'm tired with this bullshit. I'm done with this. Yeah. What else? Next will be conjugate gradient. I'm gonna like the conjugate. I like the conjugate gradient one. Well, I also liked this bullshit, but I did not. I'm unraveling. I'm going crazy now. How long has this video been? 1.5 hours. Okay. Yeah. Can I just recap iterative methods? Iterative methods are solving iteratively. Iterative methods are iterative. And this is the format. Q is the preconditioner. If Q was A, I am golden. Richardson method, Jacobi method, Gauss Siedl, and over relaxation or damping, whatever, which is like taking the omega times the new plus 1 minus omega times the old. Okay, fair enough. I'm done with this.